Good afternoon, everyone. Welcome to this session on porting finite state automata traversal from GPU to FPGA, exploring the implementation space. Let me just give some context to this session. Programmability is one of the biggest challenges for custom hardware faced by both hardware developers and software developers, regardless of how much expertise you have, unless you have a lot of it. Writing code for high-quality hardware using hardware description language such as HDL, Verilog, VHDL, it requires both time and expertise due to limited abstractions akin to assembly languages for CPUs and GPUs. High-level synthesis, HLS for short, provides an alternative to HDL programming by enabling designs to be expressed with high-level languages such as OpenCL, which is then compiled to HDL code. This is similar to the front end for compilers for software in that high-level synthesis compilers parse high-level language code to generate intermediate representation and do a number of optimization passes on this IR code. Developers can guide the optimization passes by annotating the source code to indicate where, how, and to what degree parallelism can be exploited. But despite the advantages that we see of high-level synthesis, we are still far away from the same levels of productivity as with compilers for software. And that is why research in this area of high-level synthesis is so critical. And with that, let me introduce the speakers for this session, Dr. Michela Becchi and Marziyeh Nourian. Michela Becchi is an associate professor in the Department of Electrical and Computer Engineering at North Carolina State University. Michela's research interests lie broadly at the intersection between computer architecture, system software, and applications. Marziyeh Nourian is a PhD student at North Carolina State University, working with Dr. Michela Becchi. Her research has been focused on hardware-software co-design for high-performance computing, specifically targeting large-scale pattern matching and data transformation applications. Her research interests include parallel computing, heterogeneous, and reconfigurable architecture. We will also be joined in the roundtable session after this talk by Mustafa Ekbeli, one of the primary researchers on this topic. Mustafa is a PhD student at the ECU department, working under supervision of Dr. Michela Becchi. His research is focused on the exploration of different optimizations and scheduling methods on high-level synthesis tools for FPGAs, specifically OpenCL for FPGA SDKs. And so with all that, I will hand it over to Michela, who will kick off the presentation.
Okay, great. So before Marziyeh started talking about our project on finite state automata, I wanted to provide a high-level introduction on the overall FPGA project we are working on. And actually, before we delve into it, I wanted also to provide some high-level background on FPGA in case somebody in the audience have not used FPGA before. So basically, FPGAs are a programmable hardware device, and they consist of some configurable logic blocks, and they have those configurable logic blocks are connected through a programmable interconnect. And so you can see a diagram on the bottom part of the slide. And at the high level, those configurable logic blocks contain some hardware modules that are called slice, and they have some flip-flop and lookup tables that can be used either to implement some logic or also as basically distributed memory on the FPGA. In addition to that, FPGA also have some block RAM and also some DSPs that can be used, for example, to implement floating point operations. And so at the high level, what a programmer does when he wants to use an FPGA is really to implement a particular function into hardware. And FPGA are typically considered hard to program, and they can be programmed into different ways. The most traditional way of programming them is through hardware description languages, and typically Verilog and VHDL are used. And so in this case, really what the programmer does is to define all the modules that that basically are part of the hardware specification and how they are interconnected. Now, there has been a lot of work on having some high-level synthesis tools that make FPGA easier to program, also for people who have done less logic design. And typically, they allow to program FPGA starting from some subsets of C, C++, and System C. So more recently, there has been interest in programming FPGA for OpenCL, which is a programming model used typically for GPUs, or that can be used also for multi-core CPUs. And so both Xilinx and Intel are now providing some compiler toolchain that allows to take OpenCL code and deploy it on FPGA. So from the point of view application domains, FPGA have been used successfully in networking, where basically they have been used in order to kind of accelerate the networking pipeline and implement programmable network routers. And in general, FPGA are good for streaming applications because you can think of streaming data on the FPGA and then implementing on FPGA some hardware pipelines that can basically do some fast processing on the data. And by using all the memory which is available on the FPGA board, it's possible to have a computation that happens online close to the data. So other application domains where FPGA has been used successfully has been bioinformatics, so for example for a genomics application. And then FPGA has been used also in signal processing and fast prototyping. Now, for us, our project we are working on has to do with using FPGAs in a cluster of computers along with GPUs and CPUs or even over accelerators. And so, you can imagine that we are looking at systems that consist of different nodes that communicate via over network. And each of these nodes can have a number of CPUs, a number of GPUs, and a number of FPGAs. And so we want basically users to be able to program those systems using OpenCL. And we want basically users to be able to deploy their application without wondering about how the underlying hardware works. So without wondering whether the application will run on a FPGA or a GPU. And so at the high level, what our software stack looks like is that we want to have a runtime system that sits between the OpenCL application and the hardware. And because we consider OpenCL as a programming tool for both applications, our runtime system sits on top of the OpenCL driver and runtime available for GPU and FPGA. And then the runtime system includes some basically software component that virtualize the GPU and FPGA device, includes some scheduler that will basically automatically decide whether a particular application should be deployed on an FPGA or a GPU or even split across multiple devices. And then the runtime system will also provide a sort of unified memory abstraction to basically allow the programmer to have a simple view of the whole system. Now, in order to implement some effective scheduling mechanism, we need to be able to understand which applications are good for FPGA, which are better fit for GPU. And also we want to provide some mechanism to take a GPU application and kind of modify their code so that they will also run more efficiently on FPGA. And so, part of our work has also to do with compiler support. And so that's basically the, let's say, the part of the work where this project that Marziyeh will be talking on sit. And so with this, I'm going to hand off the presentation to Marziyeh.
Okay, so basically going back to the main title of this presentation, which is porting finite state automata traversal from GPU to FPGA, I'm gonna basically go straight to the slides that are related to this part. So basically, in this work, we took an application which is finite state automata processing with a relatively large code size with FPGA-friendly characteristics, and studied OpenCL level techniques, which can benefit people with no HDL perception in order to optimize the design generated by OpenCL to FPGA HLS toolchain. So our motivation for this work has two aspects. The first one was that most of the OpenCL benchmark applications, such as Rodinia, which is a well-known one, have codes with small sizes. And we collected we have collected resource utilization of 6 Rodinia applications in terms of overall logic, utilization, RAM block, and DSP block utilizations. And the results are shown in the table that we see. As can be seen, the utilization do not go above 45%. And in general, among all data sets, resource utilization has an average of more or less 23% for logic utilization and RAM block utilization. So, and a large bulk of research basically on OpenCL to FPGA mapping use these like such small data sets. So the second motivating point for this work was that our application, this specific application that we were working on, is designed to be memory efficient and reduce the memory bandwidth and storage of basically baseline implementation of the target application. So this is helpful for FPGA because it has limited memory bandwidth. So another characteristic is that our application do not also need synchronization, which is in practice very inefficient to be like implemented and mapped onto FPGA. And the other one is that it has this application has SIMD-friendly characteristics. Just going over what is finite state automata and what's finite state automata processing. Finite state automatas are used in pattern matching applications, and they are state machines with a set of states and transitions that are traversed for finding patterns in input streams. So we can accelerate the finite state automata traversal by taking advantage of a different range of different accelerator architectures and designs. These designs may rely on logic, or may merely rely on logic or memory, or they can even rely on the combination of them. So FPGAs in specific can be programmed, for this application can be programmed to either merely use logic or it can also be designed to use a combination of logic and memory. So in this work, we have specifically used a design that relies on both memory and logic. So this memory efficient design targets finite state automatas that are having fixed topologies. I will not go through the details of automata design, but what I said simply means that only symbols associated to each transition are different among different finite state automatas. We see an example of 2 finite state automatas with fixed topology here. And at the bottom of the page, we see the topology that these automata share. Based on this, the kernel code for traversal of finite state automata includes chunks of codes that are similar among automata applications and chunks of codes that are specific to the target topology and basically to the target application that we have. So on the left-hand side, we observe the code that is basically similar among all data sets. In order to store the activation status of a finite state automata before and after processing each input stream, basically each character of the input stream, we use bitmap arrays. In general, the bitmap arrays are mainly used in traversal processes and are called current and future state vector. With current status vector holding the status of the states at each state that as the current stage that we have, and then the future status vector holding the status of the states for the next incoming stage. So updates to these status vectors are done through simple binary operations that are implemented in parallel fashion, which are basically shown by the underlying codes here. So there is also a section of the code that differs based on the topology, which is embedded in the topology specific traversal function. So we will look further onto this part of the code in the next slide. But in general, it's important to note that due to the frequency of the updates to these status vectors, they are stored in shared memory. However, the transition symbols are of different NFAs are basically large, and they are also stored in global memory. So here the code that represents the topology dependent part of the design is shown, and it basically encodes each transition of finite state automata. So not going through the details of what are different types of these transitions of finite state automata, I'm just going to overall show that each transition is encoded using two functions that are basically topology independent. The first function is called matchcheck, which basically compares the input symbol against the transition symbols and store the result of this comparison in a mask variable. For this purpose, this function basically reads symbols associated to each of these transitions from global memory. And for each transition symbol, it also checks the transition symbol of a batch of NFAs against the input symbol. So the second topology independent function is called SV update, or status vector update. That is meant to update the content of future status vector through binary operations that basically rely on the content of the current status vector and the mask variable to be able to update the future status vector. So in general, therefore, the topology is represented by encoding transitions sequentially using these functions that I just talked about in a flat manner. So as we see here for this example, these are the sequential codes that are representing these different transitions that are associated to the topology that we see on the top of the slide. So based on this, the transitions are executed sequentially, and but the kernel is parallel since each work item updates a batch of NFAs simultaneously. Here, I'm going to show some results of the initial mapping of our flat code or initial code to the FPGA using the OpenCL to FPGA toolchain. But before that, I'm going to give you a background about different types of OpenCL code, like OpenCL kernels that we have. So OpenCL kernels can be in two different forms, which are ND range and single work item kernels. ND range kernels have multiple work items and work groups, and single work item kernels comprise of one work item, and they basically have loops that iterate over the tasks that are done by work items in ND range form of the kernel. So we implemented the single work item version of our code by embedding the bug of the original ND range kernel, which was made for GPU and was GPU friendly, within a nested loop on work group and work items. And basically, each work group was corresponding to each different input streams, and each work item was basically supposed to support a batch of NFAs in parallel. So overall, ND range kernels, for the ND range kernels, the tasks of each work item are pipelined, and work item groups are executed sequentially. And in case of single work item kernels, each loop iteration will be pipelined. So the table shows this table shows the logic utilization of our initial flat code for 7 different data sets or 7 different topologies. As can be seen, the original flat code is almost always exceeding 100% utilization, and even those that are not will not be able to place and route TED on the device. So these results are therefore estimates that are provided by the Intel OpenCL FPGA toolchain on Stratix 4 FPGA. So what we see motivates us to explore a set of customized and general OpenCL code level optimization techniques to address this first issue that and other issues that basically we face later, such as excessive global memory stalls. That I'm going to talk about it later. Based on this, in order to retarget our GPU efficient code for FPGA, we studied a group of customized optimizations and a group of optimizations that are recommended by a best practice guide of the OpenCL to FPGA toolchain. Among these custom optimizations are 2 of them are generally applicable to applications beyond FSA traversal. Currently, we are also in the process of studying the effect of thread core sending optimizations for basically general applications and also this application. In the remaining part of the presentation, I'm only going to focus on the details of the first 2 custom optimizations due to the basically time limit. So, basically, for the first optimization that I'm going to talk about is structural code changes. I explained this optimization using a small micro benchmark code. On the left-hand side, we have the unoptimized case, and on the right-hand side, we show the optimized one. And the graphs are taken from basically Intel Toolchain System Viewer report, and these graphs present the memory control flow in addition to present the memory and then control flow of each module in the design. So for this optimization, we generally observed that although modules are not generated at the granularity of basic blocks in the code, control flow instructions can break the code into code blocks for module generation. Based on this observation, by inserting control flow instructions, we try to get finer grained modularity and therefore smaller designs. So as an example, for the represented microbenchmark here, the original code contains 8 load units and 4 store units. However, by dividing the corresponding code that requires these resources in 2 sections using control flow instructions, on the right-hand side, we reduce the number of load and store units by half. So in general, the more similarities among the blocks of code will decrease the size and the number of the final design modules, the final modules of the design. So as shown previously, in our target application, we have encoded transitions sequentially. And based on the likelihood of the similarities in code blocks, we added control flow statements in 3 stages. The first one was a source-based control flow insertion, in which we were inserting control flow statements between the transition of each source state. The second one was transition-based control flow insertion, in which we were basically inserting control flow statement between transitions. And the last one was the character-based control flow insertion, in which we were inserting basically the statements between the transitions. So and then basically, by showing the microbenchmark of last slide, we also showed that this optimization can be generalized. So now we can look into the memory layout change in order to optimize the throughput of the design. This custom optimization is useful for a single work item kernel. This optimization optimize status vector updates by changing the memory layout of status vectors. In the top picture, we have the original status vector layout of the code, which was designed to perform in an efficient therefore GPU, while in case of single work item kernel, the loop iteration are executed sequentially and potentially present more locality per loop iterations, and therefore we basically change the layout in the form that we see below, and in this layout we group together all the data processed by the same work item. So here we see the experimental results. For the evaluation, we used 7 data sets, and we incrementally added optimizations from left to right, and we performed these tests on 2 input streams. The different, I'm just gonna go quickly say that the first one is the first optimization structural change that we talked about. The second one is using vector type for reading large sum of memory at once. The second one is using constant memory, and the third one is stream level parallelism, that is basically just putting in multiple work groups into one work group. And then the third one is SIMD vectorization, and then the last one is pipeline replication. So as can be seen for almost all end-range kernels, the best throughput is achieved when applying all optimizations up to SIMD vectorization. Pipeline replication does not improve the throughput, possibly because of the increased constant memory miss rate. And structural code change has the most resource-related benefits compared to the other optimizations. For the single work item experience, we see that the optimizations are the optimizations are similar to ND range. There's only one extra optimization, which is the memory layout change. And the general observation is that ND range is better throughput. ND range has better throughput because we already don't have synchronization. Single work item is good for the cases that we have synchronization. And single work item also requires more resources than ND range. And on single work item kernel, the use of vector variable is the most effective optimization on the resource, basically utilization. And that's the presentation.
So I guess let me ask a question then at a higher level. So how, so the complexity of high-level synthesis versus your traditional software languages, how would you place that? What was your experience with using a high-level synthesis language? Is it as easy as Intel and Xilinx have marketed it?
Well, I think I can address that. Well, to be honest with you, I wouldn't say that it's an easy process because basically the mapping, the actual mapping between the design and the hardware is very complicated to understand. So for for finding optimizations, it's hard to get into the details of how these these designs are made to be able to have a good approach of finding optimizations. That's the whole thing. Do you Michela and Mustafa, do you guys want to add anything else to that?
I think it's worth mentioning that the general opinion, making the application or the modules you want to use work on OpenCL platform is not like a hard thing to do. But the hard thing is when you need your application to be optimized with respect to the resource utilization and throughput, or like the performance you want to get from the implemented application on your target device. Because the good thing about OpenCL platform is that you can migrate on different hardware targets without doing too much work. So that's why using OpenCL means that if you have the code for other platforms, then you can easily import that application to your specific hardware. But as I said, the bottleneck is when you need to have the best performance or the best resource utilization for that specific application.
Also, I think it's worth adding that Intel also suggests a set of best practice optimization that can apply to many applications. And what we found with this project, but also with other projects, is that some of these best practices optimization work well on, but it's really very application dependent. And so with some applications, we have noticed that best practice optimization are pretty simple. Sometimes they are automatic to make, but the return is not that much. And so, very often you get to the point after you applied all this best practice optimization where you need to think, oh, should I rewrite this particular part of my code in a different way? And so, that can be expensive, and that's where understanding how the mapping is done by the toolchain is important.
That's very interesting because one of the things that we also found out was that Intel's proposed optimizations in their best practices guide, there's an inherent assumption that the developer has a lot of hardware expertise and they know exactly when and how to use which one of them. So for example, the channels that they provide, and while they encourage, use channels, it's easier to separate out tasks into separate kernels. and they actually have a reference design for doing FFT, which is incredibly optimized, and it actually gives you close to HDL performance. But that's a design written by Intel engineers, and if when I looked at the design, it's the complexity of it. It is no longer a high-level language GPU or CPU-like code. It has turned into something very complex with all these functions and all these data structures that are hard coding in there, to the point that it was starting to resemble more like an FPGA code. So there is definitely a problem with the way Intel is doing it. But that sort of puts at least the second question. With SYCL, they're trying to move in the opposite direction. So Intel Xilinx, when we talk to them, they're moving in opposite direction. With SYCL, Xilinx is saying, we don't want to give people more options. We want to take them away. Let's have even more abstractions on top of this. Let's just let them tell us the basic stuff. And Intel is going in the other direction where it's saying, no, this thing works. We want to give even more control to the developer. We want to have them specify everything because, so for example, in 2016 version of OpenCL, it will assume that if I have enough resources, I can unroll a loop even without saying pragma unroll. But in 2017 and 18, that went away. Or I think it was in 2015. But one of the earlier versions had that capability, and then they took it out. So the question is, which direction do you think is the better path going forward? The way Xilinx is doing it with more abstractions, or Intel with less abstractions?
Okay, so, then maybe Mustafa and Marzi want also to add something. It's hard for me to think that by having a lot of abstraction, you can get efficient code. I think that, for what our experience has been is that, abstraction allows you to deploy easily, but then the code that you deploy may be very inefficient. And so, we have seen that actually if you have a code that was thought with GPUs in mind, achieving good performance on FPGA is pretty hard unless you spent quite some time optimizing the code. And so I guess that Xilinx has to come up with a very intelligent compiler, to be able to provide efficient code with a very high level of abstraction. So that's my feeling. Most of Fine Marzi has been fighting more with the tools, so they probably can add, their impression.
What you said is completely correct. And one thing is that, based on all the research that has been done in this field, we see that basically what the compiler does, what the HighLevel compiler does, is not efficient at all. And there's a lot of aspects that should be should be looked at. So I think at this stage of this whole trend, it's better to have much abstraction to allow the basically research community and everybody else find the problems and then maybe suggest better ways of dealing with them. But at the end, I think the goal is to have more abstractions, and the reason is that the goal of having these tools is allowing people who basically do not have much information about hardware to be able to use, hardware. So that's what it is.
So I guess Michela and Marziyeh covered most of the information regarding that question, but the only thing I want to add is that if we see this question with respect to the purpose of the OpenCL, then Xilinx is taking the right path, because the purpose, as Marziyeh mentioned, is just letting people with low hardware knowledge able to program the FPGAs and implement their application on the FPGAs. But there's a fact that, at least with the state-of-the-art compilers, there are not enough ability in the compilers to find the best solution for each and every application. And that's why Intel is providing different features on their OpenCL to FPGA SDK, as you mentioned, using channels or many other features, so that the programmer can use from this pool whole of optimization tools in order to find the best solution for its problem. So I guess if Xilinx wants to be succeed in his path, he should have a compiler that can get like too many parameters that can define each and every goal of the programmer for using that tool. Because sometimes you're programming for performance, sometimes you're programming for low power usage, sometimes you're programming for using fewer resources so you can like map your program onto small FPGAs. So I guess if the Xilinx want to be succeed, it should take a path that it has like a compiler with lots of input parameters that can define what exactly the programmer wants. And I think Intel believes that this path is not possible or is not feasible right now. So that's why they are giving you a pool full of optimization tools that you can pick from each and every one of them and use them in order to reach your goals for that implementation.
Actually, Ahmed, I wanted to ask you a question. So the advantages of tool like OpenCL or SQL is that they apply to GPU, they apply to FPGA. So there you want to have a common programming interfaces for many devices. However, while FPGA are good for a kind of streaming application, data flows application. So there you're taking a tool, an OpenCL, SQL, you're taking a tool that is good for kind of more traditional architecture, and you're trying to program a completely different architecture, an architecture that is not a Voight-Neumann architecture with that programming model or that programming abstraction. And so, I wonder if with FPGA, yes, it's okay to have OpenCL so that you can be compliant with other architecture, but whether it would also make sense to come up with a different computing abstraction that is better at defining, for example, some pipelines. So, a computational abstraction that maps more to what the FPGA hardware looks like and to what it is good at. Because now if I want to define, for example, my machine learning pipeline, right, I know that FPGA can be very good at it, but is it good to do it in OpenCL, right? Or should I have another abstraction, which is still an abstraction, but, maps better on FPGA?
So the way that we being me and Uli, the way that we discussed this is that so code will require annotations, absolutely. There will always be limitations in the semantics of the language that will prevent us from expressing hardware in the detail that we need. As Mustafa pointed out, it could be you're targeting performance, power, resource, any combination of the above. So there will always be parameters or pragmas or annotations specific. But the type of language that we are thinking of is more traditional. Taking things like C code, annotating that with OpenMP pragmas to show where the parallelism is potentially present in the code, to show which loops would benefit from an unroll, or how, or really, what would you want to parallelize based on your specific requirements. And then our goal is to actually provide the compiler with a reliable way of measuring what it is currently unable to measure, and that is performance, or really the impact of any optimization it does in the context of an FPGA. Because these compilers, these optimization passes, they will target CPU or GPU because that's what they were written for. At a higher level, that's what these compilers and these optimizations were built to target. But the FPGA provides a whole unique set of design parameters, or design patterns, I should say, that the traditional compiler doesn't know how to handle. And that's why Intel relies on all these different things that the developer has to then step in and tell, turn this loop into this, turn this into that. And so if we have a model for an FPGA, something that you can tell that if my intermediate representation or my data flow graph looks like something like this, this would map to an estimate of X performance on the FPGA and Y resource usage, and so on. And that's what I tried to look at in my dissertation. And surprisingly, it showed some positive results. That if you can tell, even the 10 basic things we looked at, SIMD, pipelining, hazards, just a very basic thing that you can sort of detect by looking at the data flow graph. If a compiler can see that stuff and the compiler can then optimize accordingly, you don't even need to change the compiler itself. You can just change the high-level code structure. So, for example, we did a C2C compiler. So we wrote OpenCL code, and then we empirically or iteratively modified that to bring it into form that the compiler could then all of a sudden see all the optimizations that it was supposed to do. Because inherently, an FPGA architecture is not too different from the CPU and the GPU. It's still trying to do some basic optimization. There is some overlap. There are some very specialized ones, and Intel thankfully does have some very good passes that attempt to target those. But it was missing out on those some common optimizations that you would do regardless of the backend, but it was not doing that well for the FPGA. So yes, languages have limitations, and we think that having a high-level language like C is certainly going to be the way forward, because this will mean that it's usable not just by people who are writing new code, but it is applicable to all the legacy code. Yes, it will require some annotations. The less, the better. But I think OpenMP is good enough. It does provide enough control over the code that an FPGA will be able to express that. And the big piece that's missing from all this that isn't done today is a way for the compiler to gauge how good or bad any optimization would be, rather than rely on the developer to do it, compile everything to hardware, test it, and then find out, oh, this didn't work right. So that's the sort of, that's my thoughts, and that's our thoughts on this.
Speaking about C or System C, do you have experience with Xilinx Vivado? Because I think they put quite, some effort, right, in that tool.
Vivado HLS?
Sorry, Vivado HLS, yeah.
I haven't used that yet. I was using Intel OpenCL.
Okay. No, because, it would be interesting
to use Vivado, like, just since you asked about Vivado, I used to use Vivado during my undergrad, and it is almost like the same environment, but it is like more, how can I say, it's more personalized for Xilinx, in the Xilinx platform. So it's still the same concept as writing the C code using some annotations or pragmas in order to add some more FPGA specific optimizations, but still the concept is almost the same as the OpenCL.
So did you get a sense of, what it does, what is it that it does well, and what, where the weaknesses are? You spend some time also with the OpenCL compiler, right? And, you've seen that you had to do quite some analysis, to get good performance. And it's interesting that Ahmed was talking about channels, because also Mustafa spent a lot of time on channels. And we were expecting better results, from using channels than we have actually found. And so when probably it was undergrad, probably you didn't have time to do much evaluation, but did you get a sense of how much of hand tuning you needed to do to get performance out of Vivado?
Yes, the steps were almost the same. OpenCL, we didn't do too much evaluation. We just had we just had some simple optimizations that we applied to our base kernel, the kernel synonym in Vivado HLS. But I guess the steps were almost the same. That like for example, we added some optimizations like unrolling or some other optimizations, and then we inspect to see like how it impacted the performance or impacted the resource utilization or the power usage. But in the high level sense, I don't think there's too much difference using the Vivado HLS with the C or C or C++ support, and using OpenCL for Intel OpenCL to FPGA SDK.
So
I
I'm a part of
had a couple of,
Mhm.
just a couple of things I mentioned there. One of the things I do like about the Xilinx tools is the simulation aspect. So the regular Intel OpenCL tools, they provide hardware emulation, which is great if you want to check for deadlocks, if you want to check for all these sort of high-level things, but they won't really tell you much about the cycle-accurate performance. They won't show any waveforms. But with the Xilinx tools, you are able to actually do a cycle-accurate simulation of the design, which does give you a lot more feedback, and you don't have to spend a lot of time designing hardware to get that information. And with channels, one of the reasons why channels are so hard to use is because it doesn't do global optimizations with them. So we had a paper at Heart where we tried to implement FFT with this, and when we try to do this with channels, every stage in the FFT was implemented as a separate module with the channel being a FIFO between them. And when it automatically inserts a FIFO between two modules, it will not do a global optimization for the logic. It will optimize each module separately, which will, of course, be limited in the benefits that you can actually versus the ideal benefits you would have gotten. But when I put everything as in a single work item kernel, no channels, single kernel that's going to do everything, it actually did some very interesting optimizations. So it wasn't even the case where it was taking each computation and doing a one-to-one mapping, but it sort of reordered the pipelines, it reordered the delays, it cut out a lot of them. It was pretty efficient. So that was a surprising thing, that the compiler is able to do a lot, but all these optimizations, if used incorrectly, can actually make the program worse than if they were never used at all, because they will block optimizations when they're used. And channel is a big example of that.
So Ahmed, part of what you were proposing is combining the compiler with auto-tuning. So for example, the compiler could generate different code variants and then you run them to understand which is the best code variant for this particular application.
Yes,
then I have a question.
Yes.
So you were talking about, your analysis that you did with channels. So Marziyeh and Mustafa were using the system view and, in general, all the kind of profiling from the tools to try to understand how the hardware that is generated looks like. Did you also dig into the Verilog file, or, at what level did you work to understand what was going on?
No, I spent 2 months following wires across my screen. It was painful, but that's how I was able to figure out exactly what it was trying to do in the background. And that's where I saw all this channel stuff, the impact. So I used to modify the code, compile it, and then trace the wires throughout to see, how what I was doing here translated to there. So for example, what happened if in my kernel input, I don't pass it a vector or a pointer, but I pass it a constant? How does that constant actually get applied to my kernel? Similarly, what happens when I do a single work item versus multiple? And then this observation with channels that we had was again looking at the Verilog code and saying, well, I took away the channel. How did the code look like after I was done?
So basically you did both. You both, look at all the wires, and then you also look a little bit into the Verilog.
And then that's where we did the what's the HBEC paper, which was basically if you can look into the Verilog, then you're just one step away from supporting simulation, which is, if you can see the Verilog, just cut it out and turn it into a test bench. And then you can overcome one of the biggest limitations Intel had back then. I'm not sure if they've addressed it now, because they keep improving their toolchain. They're adding more and more insights. But the 2016 version that I used had absolutely nothing in it. was the very bare bone version of their HLS compiler.
I think I haven't worked with that, but they also have a simulator that you can use Model Sim to simulate your kernel. But as I said, like I never used that, so I don't know how hard it is to get it to work. But they support that, and they are recently, after like launching their compiler, they are also like adding tools that can help the programmers to understand more about what's going on inside the hardware, rather than just having some high-level knowledge of the like how many resources are used, or how much resources are used, or like what is the final performance of the kernel.
Oh, great! So they finally did add that. It was very surprising that they never had it to begin with, just because it's such a critical part of the process. But I'm glad they added it in the models and simulation. Well, I think we're at the top of the hour. So again, I'm gonna thank you so much for the presentation. It was wonderful.
Well, thank you,
And,
Ahmed, for all the information you gave us, and also for letting us present and lead our presentation.
Thank you. It was wonderful. It's really happy to see that there's more FPGA talks now at these events, and hopefully there will continue to be more and more over the next events.
Marziyeh is graduating soon, but Mustafa is working on this FPGA project, and so for sure he will look into your dissertation and your paper. So you may be hearing back from us with questions.
Yes, definitely.
Happy to be involved in this stuff. This is all really important stuff, and without high-level synthesis working properly, it's going to be very difficult for software developers and a majority of hardware developers to be efficient with these tools. So this is a very critical piece of the Open Hardware Initiative.
Exactly.
Okay, great. So have a nice day.
Thank you.
Thank you, guys. Bye-bye.
You too.
You too.
Bye-bye.
Bye.